before we move on, I just wanted to make sure you understood that last point I made at the end of that last video. We said that the pressure kind of inputting into this, we could view this cup with a hole in it as essentially a pipe, where the opening on the top of the cup is the input to the pipe, and this little mini hole is the output to the pipe. And we said that this is a vacuum. Let's say this is a vacuum all around. I know when I drew it last time I closed it, but maybe we have a vacuum everywhere. And since there's a vacuum everywhere, the pressure at this point, P1, is equal to 0. And the point I wanted to make is, because we have a hole here, the pressure at that point, at P2, is also equal to 0. You can almost view it as maybe the atmospheric pressure at that point, but since we're in a vacuum, that pressure is 0. And that might have been a little confusing to you, because you said, well, wait, I thought at depth, if I had a point, let's say at that same height, that I would actually have a pressure at that point of rho GH. And that's true. That's completely true. You do have an innate pressure in the liquid at that point of rho GH, and actually that's what's causing the liquid to come out. But that's actually taken care of in the potential potential energy part of the equation. So let me rewrite Bernoulli's equation. The input pressure plus rho GH1 plus rho V1 squared over 2 is equal to the output pressure plus rho GH2 plus PV2 squared over 2. And I think you understand that this term is pretty close to 0 if the rate at which the surface moves is very slow if this surface area is much bigger than this hole. So it's like if you poked a hole in Hoover Dam, that whole lake is going to move down very, very slowly, like 1/1,000,000th of the speed of which the water is coming out at the other end. So you could ignore this term. And then we also defined that the hole was at 0. So H2, the height of H2 is 0. And so it's simplified down to the input pressure, the pressure at the top of the pipe or at the left side of the pipe, plus rho GH1. And this isn't potential energy. This was kind of the potential energy term when we derived Bernoulli's equation, and that equals the output pressure, or the pressure at the output of the hole, at the right side of the hole, plus the kinetic energy, PV2. The kinetic energy term, because this actually doesn't add up completely to kinetic energy because we manipulated it. And I just wanted to really make the point that this is definitely 0. I think that is clear to you because we have a vacuum up here. So the pressure at that point is 0, so we can ignore that. And so the question is, what is the pressure here? And I said, well, this pressure is 0 because we have a vacuum here. If I were to say that the pressure over here at this hole is equal to PGH, let's say that I said that the pressure at that hole is actually equal to PGH, where this is H, then I would have the situation where PGH is equal to PGH plus PV squared over 2. And what does that mean? That when I say that pressure at the output of the pipe is PGH, that means that I'm applying some pressure into that hole. And essentially, that pressure I'm applying into the hole is exactly just enough offset to pressure enough offset to offset the pressure at this depth. And because of that, none of the water will move. You can imagine if this is the hole, let's say that's the opening of the hole, and I have some water particles or some fluid particles. Let's say that these are the atoms. These are the atoms. We're saying innately at any point, let's say at this, sure, there is a pressure at this point that's equal to rho GH. But this is P2, how much pressure I'm exerting on this end of the hole. This is P2. And if I exert rho GH at this end, if I exert rho GH at this end, then these molecules that are just about to exit the hole aren't going to exit because they're going to get the same pressure from every direction. So what we said in the last video, and I really want to, because this is a subtle point, is that the outside pressure being on the outside part of the hole is 0. And because of that, we end up, this term is 0, And we essentially end up with the change in the potential energy all becomes kinetic energy, which is something we're familiar with from just our kinematics and our energy equations. Well, anyway, with that out of the way, let me do another problem. And actually, I will do that next problem in the next video, just so we have a clean cut between videos. See you soon.